Next speaker is Abhishek Dhar, and he's going to tell us about non-Hermitian description of the Quasi-Zeno dynamics of a quantum particle. So could you go ahead?
Yeah, thanks. So first, I would like to thank Manas and Bhabani for this really nice program and for the invitation. So what I'm going to talk about is what is called the quasi-Zeno dynamics of a quantum particle, and the fact that this can be described by a non-Hermitian Hamiltonian. Okay, so mostly I will talk about work that's done with my student Varun Duve and a colleague at University of Nice, Cedric Bernardin. But some earlier work was done with this set of people. So these are now published in these papers, and the latest work is supposed to appear in this PRA. Okay, so let me explain what the basic problem question is. So let's imagine the following problem. Like we have, so we are in this room of size L, and initially we have a wave function which is localized in some, so it's localized in some small region. And at time t equal to 0, we let this we let this wave function evolve from this, starting from this localized state. And sorry. Yeah, and then we have some measuring device in this region D. So this is what I'll call the measurement region, and then I want to. So this is somehow, it might be a cloud chamber or something, and as soon as a particle hits it, I mean there's a signal, right? So we want to ask the question after at when do you first hear a click? Okay, so when is this particle detected for the first time? So that is the question. So more precisely, what is the probability PTDT that the detector clicks and thus the particle is detected for the first time during the time interval T2 T plus dt. So since it's a probabilistic, I mean, quantum mechanics is a probabilistic system. So we expect that the time at which you hear a click should not be a fixed number. It will have the distribution, right? So we want to find this distribution. And related question is like, how long does the particle survive from being detected? Okay, so these are the questions, and this probability of first detection is related to the probability of survival in this way, because the decay of survival probability means that it has got detected. So this is some obvious relation. Okay, so these are the two questions we are interested in. What is the probability that the particle gets detected between time t to t plus dt, and a related question is what is the probability that it survives being detected till some time. So this is the main question we address, and it seems a reasonable question from the point of view of experiments. And what I'll try to explain is how do we calculate this from quantum theory. Okay, so there was an earlier talk by Eddie Barkay, and he also discussed this same question. Okay, so if you want to just think of some experiment in mind, you can think of like these experiments where people do with cold atoms. So you start with a trapped set of atoms, and let's say, so there are experiments where you release the trap, and then these atoms are all falling freely, and then there's some detector region, and typically what people ask is like, what is the distribution of times at which you hear clicks on the detector. Okay, so this is an experiment people actually do, and we want to understand this within the framework of quantum mechanics and measurements. Okay, so like Eli had mentioned in his talk, I mean, this is similar to the question of the so-called Polio problem for random walks. So there, I mean, if you have a random walker, you can ask what is the probability it reaches some point for the first time. Okay, and and then you can ask things like what is the probability that it ever reaches a point. Okay, so in one dimension we know that for a random walker the probability of reaching any point is 1. It will always reach any point with unit probability, while in higher dimensions this probability is less than 1. In dimensions greater than 2 it's less than 1. Okay, so now, I mean, so in for a particle executing random walk, the probability distribution satisfies the diffusion equation. And now, if you look at a quantum system, it is similar, but we have a wave function which satisfies sort of diffusion equation with an imaginary time. And so the probability distribution is given by mod psi square. So this is one difference with the random walk. But one big difference with the random walk is that in this case we have to we have to talk about measurements, and whenever we make measurements in a quantum system, it changes the state of the system, right? So this is very different from a random walk. For a random walker, if we don't detect a particle at some measuring site, it doesn't affect the particle's dynamics. But for a quantum system, it makes a big difference. Okay, so basically, what we want to do is we want to use the following rules from quantum mechanics to try and understand this question. So first of all, we know that the wave function is evolving unitarily following Schrodinger's equation. And then we have to use the measurement postulate. And here in this talk, we'll just talk about projective measurements, which are instantaneous. So if you make a measurement of some observable O, then what quantum mechanics tells us is that the system, you will measure one of the eigenvalues of the operator O, and after the measurement, the system will be in one of those eigenstates, right? So the measurement postulate gives us the probability of each outcome. What is the probability I measure particular eigenvalue of O in this experiment? And it also tells us what is the state of the system immediately after the measurement. Okay, so now given this rules, question is, can we compute the time of first detection of a quantum particle? Okay, so please stop me if you have any questions. Okay, so this is the sort of schematic of what we want to do. So again, we start with some initial wave function. And so I'm talking about a system in one dimension. And then there's a detector at this point, which is like an absorber. And so the system evolves, let's say after time t, this is what it looks like. So it is now spread over the detector. And now I make an instantaneous measurement. And after the measurement, there are two possibilities. I either so this my measurement operator is now is precisely this is the particle in this region or not, right? That's the observable. So the outcome of the measurement can be either I don't detect the particle or I detect the particle. Okay, so if I don't detect the particle, even then the state of the system changes. It's now so I know it's not in this region. So the wave function immediately after measurement will now actually look like this. Okay, so it's kind of chopped off in some region. And if I detect, then the system is given by this wave function. Okay, so measurement, even a null measurement where I don't detect the particle, changes the state of the system. Okay, so now, if you want to really ask this question, when is the particle detected? And we are doing this instantaneous measurements, then what we have to do is we have to do a sequence of measurements. And every time we ask, have we detected the particle, yes or no, right? So if the answer is no, then we know that the state is this now. And we have to again evolve it unitarily for some time, and then again make a measurement, and so on, right? And we stop the experiment once we make a detection. Okay, and then we say that this is the so the time of first detection is this is the first detection event. Okay. So I hope this protocol is clear. And so now what we want to understand in this talk is how does this
Abhishek, can I ask a simple question here?
Yeah.
Even your wave function is spread over the detector, then there is also possibility they may not detect it, right?
Right, yeah.
So I don't understand the bottom picture, what you want to say here.
No, so I'm saying, yeah, so like you said, there's a probability that you don't detect the particle. So supposing you make a measurement and you don't detect, right? So that means that immediately after the measurement, the system is in this state.
Okay.
Right?
Okay. Yeah.
But now you want to continue your experiment. So you want to make another measurement to see has the particle arrived.
Yeah, I got it. Yeah.
Right. Yeah. Okay, so the main point is that the state gets changed. Okay, so like under free evolution, it looked like this, but immediately after this instantaneous measurement, which gave me a null answer that it's the particle has not arrived, the state has changed. Okay, and now I have to continue with this state until I make a detection. Okay, so now we want to, so we see that the dynamics of the system under all this sequence of null measurements is a different dynamics than the unitary dynamics, and we want to understand this dynamics. Okay, so I mean, this is one of the first papers which sort of looked at this question in 1969, Alcock. Okay, and yeah, so there is a series of 3 papers actually which discussed in great detail this question. Okay, so let me now do a more precise formulation of the question. And for this, we will now work with a system with a finite Hilbert space. So let's say there are states which are labeled 0 to n. So this is how I labeled my states. And let's say I have some Hamiltonian like this. I mean, you can think of it as a tight binding Hamiltonian, which with tunneling between states R and S. But it's actually just a most general Hamiltonian with basis states given by RS, right? And the unitary dynamics is then psi t evolves in this way, and where the unitary operator is just e to the power minus iht. Okay, now we for our remember we had a detector region, and yeah, so we had a detector region, and in this case, I'll just select one state as the detector region. Okay, so let's say the state 0 is my detector region, and it could be the location of detector for quantum particle moving on a lattice, but in general, it's any target state. Okay, and now so corresponding to the measurement, I have to define an operator, and in this case, because I'm asking for the position, it's a position measurement, so the corresponding operator is exactly this, right? Okay, so so this projector operator corresponds to measurements to detect if the system is in state 0. If state is psi, then probability of detection is okay. So this is just usual quantum mechanics. At time t, if the state is psi, the probability that it's in state 0 is this, but I can write it as expectation of this projection operator. Okay, and then so this is a projection into the detector state, and then I can define this complementary projector which projects into the remaining subspace of all states which are not part of the detector, right? So 1 minus a is the corresponds to non-detection of particle in T. Okay, and you can check that this satisfy usual projection operator relations. Okay, so probability of non-detection is then given by just the expectation value of this complementary operator in the state psi. Okay, and this is equal to 1 minus p, which we of course expected. Okay, so now what we want to do is we want to write the dynamics under, so we want to do a series of measurements, and every time we either detect or non-detect. If we don't detect, we want to evolve it further. And yeah. So let's say the wave function immediately after measurement, we call it psi plus. And this, as we said, is given by A into psi if the particle is detected, and it's given by B into psi if the particle is not detected, right? So I mean, so it's after the measurements, it's projected into either of the two spaces. Okay, so this is like it's projected into this subspace or projected into this. So there are two possible outcomes immediately after the measurements, and this I call is psi is denoted by psi plus. Okay, so after first measurement, I mean, what we do is if we don't detect the particle, then we need unitary evolve the state psi plus until the next measurement. Okay, so now we consider a sequence of measurements which are made at regular intervals of time tau, which continue until a particle is detected. And so the time evolution is basically then a sequence of unitary evolutions followed by projections onto the subspace corresponding to B. Okay, so it's a conditional evolution conditioned on the fact that every measurement lead gives a null. I don't detect in the region A, and it's projected into the subspace B. Okay, so what one can see is therefore, if I write as psi n minus the wave function immediately before nth measurement and psi n plus as the wave function immediately after nth measurement, then I have this, so from n minus 1, I evolve unitarily and get at n the state. Then I do a projection and this is my new state, right? Okay, so if we keep iterating this, then we get the state that has survived detection after n measurements, and this is given precisely by this state. Okay, so instead of the usual free unitary evolution, which would have given me u tau to the power n, what I have now is evolution by this operator u tilde, which is given by b u tau b. Okay, and this you do n operations, and so this is the new dynamics. Okay, and then you can show with a bit of calculations that the survival probability is actually given in terms of this wave function. So this is now, you can see that it's not a normalized wave function, but this is what is useful for calculating the survival probability. Okay, because so since the every time you project out, do some projection, so the probability is decreasing, and the norm of this wave function basically gives us precisely the probability that the state has survived at the nth measurement. Okay, so now basically we want to then understand the dynamics of this operator with u tilde. It's a non-unitary operator, and which makes the analysis non-trivial. Okay, so maybe I'll skip this. Yeah. Okay, so now I just want to mention one thing, that okay, so we are making these measurements at regular intervals of time tau. Now, if you, I mean, ideally we want to look at continuous measurements. So you want to take the limit tau going to 0, but but you want to keep n into tau finite, right? This is the total time evolved. Now if you do work in this limit, that what you find is that the survival probability is 1 for all times, okay, and the particle is never detected. So this is a bit counterintuitive if you think about it, but this is what happens, and this is called the Zeno paradox, and it has been pointed out, I think, first by Alan Turing in quite early, but it described extremely in great detail in this paper by Mishra and Sudarshan. Okay, so that is the Zeno limit, where you take tau going to 0. But if you take a finite, consider tau to be finite, then you get much more interesting physics. Okay, so then actually you let the system evolve, but you're also probing the system. And in this case, you don't get the Zeno effect. And you can ask many interesting questions. So some of the interesting questions are, what is the evolution of the system, of this system which has survived the detection? What does it look like? And then this detection time distribution and survival probability. Okay, so let's explore this question of what is the this Quasi-Zeno dynamics is given by this evolution operator, and we want to understand this. Okay, so this is let's say this is the kind of simple model that one can consider. So here, let's say the detector site is at 0, and this is what I would call my system. And initially, I could have a wave function which is located at, let's say, site 7. It's some state like this, and it evolves, and I ask when is it detected, right? Okay, so okay, so one simple thing that one might try in the limit that tau is small is to just do perturbation theory, right? So, I mean, diagonalizing this full operator is difficult. So for small tau, if we, let's just try perturbation theory. Okay, so now so it's useful to split the, so I have a full Hamiltonian of the system. So I can split it up into what I call the system part and what I call the measurement part. In this case, just the site 0. And then there's some coupling between the system and measurement device. Okay, so the system has some Hamiltonian like this. The device has just an on-site term, and this is the coupling between system and yeah. Okay, so now if I take, so if I just take this limit, if I look at this operator, and do an expansion of e to the power minus iht, then I get something like this. Okay, so up to tau square, I get, if I just keep terms still order tau square in this expansion and neglect all these terms of order tau cube, then what one finds is that you can rewrite this as exponential of some non-Hermitian effective Hamiltonian. Okay, and okay, and this non-Hermitian effective Hamiltonian essentially looks like this. So it is the usual system Hamiltonian plus some effective Hamiltonian, which is imaginary, and basically it corresponds to the particle moving from system site L to the detector site and then coming back. Okay, so it's a second order effect, so that's why it has this structure. But this is the effective Hamiltonian that you get. And so, of course, one question is it okay to neglect the higher order terms in the expansion? Okay. But supposing we do this, just heuristically, we do this and look at, now it's a much easier problem, right? You have some simple effective Hamiltonian rather than these complicated projection operators. And we can ask what can we find from this effective Hamiltonian? 20 minutes. Okay, good. Okay, so in some earlier work, what we had done is that what we had found is that this perturbation theory is actually surprisingly accurate. So you can this simple lattice model that I talked about. This, of course, you can just study numerically. It's very easy to evolve it and then do this repeated projective measurements. And you can compare them with what you get from the this non-Hermitian description. Okay, and what we found is that they give surprisingly accurate results. And then there was some very interesting work by this set of people, including Eli, who gave the earlier gave a talk here. And what they so in their in one of their early works, what they showed is that you can also derive this problem using a quantum renewal approach. Okay, so this is very similar to what one does for the random walk. And what's nice is that you can do it completely exactly. Okay, and then we found that actually you can the results what we get from the perturbation theory and what we get from this exact renewal approach, also they agree in many quantities, especially asymptotic results. Okay, so that was really nice and good. Okay, so now what I'll talk about is so then what one wants to understand is why this perturbation theory works so well. And in this new work, what we have done is that actually this becomes this perturbation theory. You can show that it becomes kind of more almost exact if you assume that the coupling between this detector and the system is very strong. Okay, and strong means it actually has dependence on the time between interval measurements tau. So this coupling actually depends on 1 by square root of tau. Okay, so I mean, so one way to think about it is these are extremely strong pulsed measurements or something like that. So if we take this particular form of the coupling, then we can show that we get this exact non-Hermitian form. Okay, so this is what I will now describe. Okay, so this is just a summary of what all we've obtained in this new paper. So one is this rigorous derivation of this non-Hermitian Hamiltonian, where we need this particular large system detector coupling strength, and in particular this form. And in this case, you can take the tau going to zero limit, whether running into the problem of the Zeno paradox. This is one example where we worked out a lot of things, and you can do many things analytically. The effective dynamics that you get is exactly this equation. So it's free Schrodinger equation, the lattice Schrodinger equation on most sites at the site which is just connected to the detector. There you have an additional so this should be Kronecker delta of 1n. Okay, so this is a typo. I mean, it should be delta 1n.
So Abhishek, this is now for nearest neighbor hopping, right?
This is the original Hamiltonian was just nearest neighbor hopping, right? Yeah.
Oh,
And so yes, it's just nearest neighbor hopping, and there was a detector site, and now we have an effective dynamics where you can forget the detector site, and it's just dynamics on the system. But now there's an extra imaginary potential that you get on the on this site which connects to the detector. Okay, so that's the main result. So this strength of this imaginary potential is gamma by 2 plus IV, where gamma is related to the system. So it's just the system reservoir coupling. Okay, so this is one result that we have. And the other sort of interesting result that we get is usually this problem is very hard to do in the continuum. But what we managed to do is that we can take the continuum limit of this lattice problem. And then what we find is that it reduces to Schrodinger equation with what are known as complex Robin boundary conditions. Okay, so usually we have like the wave function vanishes at, let's say, the boundary. In fact, if you took the Zeno limit, you would get exactly that. I mean, the particle is almost like the detector acts like a hard wall, and the particle just freely works with a hard wall here, right? But now in this quasi-Zeno limit, what you get is a sort of Dirichlet and Neumann mixture of those boundary conditions. And so this non-hermiticity is captured in the boundary conditions. Okay, so this is what the main results in this paper. And then we, of course, discuss various consequences of that follow from this dynamics. Okay, so what I'll do now is sort of give an outline of how to derive this non-Hermitian Hamiltonian, which is okay, it's reasonably straightforward. Okay, so first of all, we can do it quite generally, and the idea is that the system and detector sites. Okay, so it's not really a so it's so there's a detector region, and you're making measurements on that region, right? So it's not really a separate detector that's coupled to the system. So it's the Hilbert space is a direct sum of the system and detector sites, and okay, so and let's say I labels all the states on the system and alpha labels all states in the detector. Okay, so this is my completeness is given by this set of this relation. And the Hamiltonian, as before, is it consists of a system part, a detector part, and a coupling between system and detector, right? And then my projection that happens after every measurement is that I project into the system subspace, right? So this is a system subspace, and I project after every measurement at time tau. Okay, and then what we want to do is we for the system detector coupling, we want to choose this special form of the coupling where it's the coupling strength scales as 1 over square root of tau, right? Okay, so right, yes. So this scales as square 1 over square root of tau, and now we again do the same expansion. So this is the evolution operator, and we expand, and okay, and then using this particular form of h, if we do all this h square and everything, then what we get is basically something like this. So we expand, let's say, up to order tau square. Okay, so there are of course tau square terms, and there's an imaginary part which is also order tau. Okay, and this imaginary potential, the strength is now given by basically again the same form. It corresponds to the system going from the system, the particle going from the system to the detector and coming back. Okay, so it has this form, and we know that it's a positive definite matrix. Okay, so now once we have this evolution operator, we can we want to take the continuum limit tau going to 0 and going to infinity with keeping time finite, and now the wave function is given by psi of n tau, right? So so now you can see, let's say psi if we want to find this, so now we want to, so there's a discrete dynamics, but we want to go to the continuum limit. And so we can try to find this time derivative, which is defined in this way, right? So the measurement, the wave function at time n minus the wave function at time, n plus 1 and n divided by tau. Okay, now this wave function is given by u tilde times this wave function. So I can write this as u tilde minus the identity operator by tau into psi. And I want to take tau going to 0 limit. And then I have this expansion. And now because I'm dividing by tau, so I can, this tau square or other terms go away. And so I can precisely take the tau going to 0 limit. And then this is an exact equation in this limit. Okay, so so now yeah.
So Abhishek, so this renormalization of your coupling that you did is precisely then making this correction to the linear order of tau, and that's how you get the effective Hamiltonian correct. Is that the right statement? Because
right, yeah,
earlier
yeah.
I
So
think it was tau
otherwise,
square.
yes, right, exactly. So
Okay.
otherwise I would have a tau square, right?
Okay.
Yeah.
Okay.
Yeah, so this is the precise point. And in that case, I mean, this term always goes to 0 in the tau going to 0 limit, right? Yeah, precisely.
Thank you.
Okay, so this way we have now a well-defined limit, and we get this dynamics. So note that, like Bijoy just said, I mean, if we keep the couplings finite, then we would get the Zeno dynamics where the particle is never detected. Okay, but if you do this limit, then you have a non-trivial dynamics described by this non-Hermitian Hamiltonian. Okay, for the specific example of this 1D lattice, we have, this is the system Hamiltonian, right? So this is just hopping between different sites, and I also include an on-site term, and there's a special on-site term at the site 1. This is just to make the various limits kind of well controlled. And then this is the coupling between the system and detector. Right, so this is the coupling. Okay, so the so if we follow our previous prescription, then we get this effective dynamics where there's a free Laplacian or discrete Laplacian giving evolution on the system, and then there's a imaginary potential at site 1. Okay, and this imaginary potential is related to this various constants. Alpha is the kind of coupling strength, and beta is this parameter that I have introduced. Okay, so so here note that the dissipation is basically given by minus I alpha, and this makes sure that the wave function will always decay and not blow up. Okay, so it's always a sink term, and there's no source. Okay, so alpha is always positive. Okay, so this is the dynamics, and then the other thing that one can do once you have this is that one can take the continuum limit. So the idea here that one uses is that the discrete lattice equations can actually be written in the following way. I can, for sites n greater than equal to 1, these are the equations. And then I can just put the this additional term that I had out here. This I can actually put as a boundary condition. Okay, this term and this term. This can be put as a boundary conditions by I mean this boundary condition. Okay, so if I put this boundary condition plus this equations, then it's identical to the dynamics given by this lattice Hamiltonian. Okay, so now with this form, it's easy to take the lattice limit, a continuum limit. So I imagine that there's a spacing between lattice sites, which is epsilon, and then the wave function will, of course, I mean, just to get the dimensions right, there's a epsilon half factor. And then if I work with this object, from this equation, I can see that I get, if I take epsilon going to 0 limit, then I get the usual free Schrodinger equation. And this particular boundary condition now reduces to what are called as Robin boundary conditions, which is a mixture of Dirichlet and Neumann boundary conditions. Okay, and then there's this parameters.
Abhishek,
yeah,
you have in the boundary condition 2 terms. So do I understand correctly that the second one with this zeta equals 0, that would be the usual Zeno limit, and because that would be like a particle in a box or something
exactly,
like that?
yeah. Right, yeah.
Okay.
Yes, zeta equal to 0, it's like that would give me a hard wall, and it's the Zeno limit. So there's no absorption. So the absorption is given actually by the imaginary part of this zeta.
Okay, thank you.
Yeah. Okay, so now, so this is the, I mean, what we get from the various limits, and let me just describe some physical quantities that we can compute now once we have this nice non-Hermitian equations. And so we have exact expression for things like the survival probability that the particle is never detected. And one interesting result is that so in 1D, I said that particle will eventually always get detected, right? So the survival probability at infinite time is 0. But in this case, for the quantum case where you try to detect a particle, there's a finite probability that the particle is never detected. Okay, so the wave function just keeps moving far away from the detector site. And then you can ask what is the probability of first detection at time t, and we found that this actually decays as 1 by t cube, which is different from the random walk, which is 1 by t to the power 3 by 2. And again, this was first pointed out by Eli and co-authors. Okay, so so one other interesting fact is that actually in this continuum case, what you can show is that there are special choice of initial wave function for which you can get, instead of 1 by t cube, you can get a higher decay rate. For example, you can get 1 by t to the power 5. Okay, so for some very special choices of the initial wave function. Okay, so these are just some numerical results showing, for example, how does the survival probability decay with the coupling with the detector. Okay, so I mean, so this actually depends on which site you start from. If you start from the site just next to the detector, then this probability decays with the detector strength. But if you start from a site which is far off, then both large alpha and small alpha give you the Zeno limit. So this is again a bit counterintuitive. And this is just some numerics showing how this probability distribution looks like, and this 1 by t cube decay law that that can be obtained analytically. Okay, so yeah, so there are some very interesting oscillations and so on, which is like which you will never see in a classical system for the first detection probability distribution. Okay, and one other very interesting question is, like, there's a surviving wave function which is evolving. What does it look like? And this we can again compute. So in this case, actually, for the non-Hermitian Hamiltonian that you have, you can compute the exact eigen spectrum, both the wave function and the eigenvalues. And for some parameter regimes, there are also bound states and so on. So it's a very interesting spectrum. Then you can solve for the evolution of the wave function of this under the condition that it's not detected. And this is how let's say if you start from a box initial condition, then this wave function after some time is given by this, and then after a later time it's evolving. So it's getting detected, and it's decreasing in norm because things are getting absorbed out here, but and the wave function is spreading, right? So that's why, because there's a kind of ballistic spreading, so there's a probability that it will actually never get detected. Okay, so this is different from the classical case where this would evolve diffusively. Okay, and this at long times, if you look at the wave function, which is plotted in this inset here, it does something, so it's evolving at long times. And then what you can do is you can ask, is there some scaling? And in fact, there's a sort of nice ballistic scaling, and you can compute the scaling functions and so on. Okay, so this scaling is valid only on x at order of time t. If you look at a smaller scale, then there's a different scaling. So in this region, there's a different wave scaling of the wave function, which leads to this absorption of and the decays and so on, right? So if you take this wave function, this has no decay, but in this region is different, which leads to the decay. Okay, so I'll just summarize. So basically, I discussed the problem of finding the time of arrival of a quantum particle into a specified region And for this, we followed the protocol of making repeated instantaneous measurements to detect if the particle is present in a specified region. And if you make continuous, usually if you make continuous measurements, you never detect the particle, and this is a Zeno effect. And what we looked at is quasi-Zeno dynamics, where the time between measurements is small but finite. And then what we showed is that this non-unitary dynamics can be described by a non-Hermitian Hamiltonian. Okay, so I think since I'm running out of time, I'll just leave this slide open. And so I just want to point out this is this paper is there in the archive, and it should appear soon in PRA. So I'll just take questions.
Okay, thank you, Abhishek, for the very nice talk. And now it's time for questions and comments. So, Jacob Bennett, could you unmute yourself and ask question?
Hello, can you hear me?
Yeah.
Okay. So I had two questions. So firstly, the boundary term that you get in your effective Hamiltonian has the form of a loss term, which makes sense because it's absorbing the particle as time increases. Can you get a gain term from this kind of setup?
Yeah, that's an interesting question, but I mean, so yeah, no, that's a question we had. But yeah, right now I don't know how you'd get. So you'd need a source, really, right? I mean, so yeah, this is not clear. Like microscopically, how you can get a source term? Yeah, this is not clear.
Right. And then my second question is, let's say you have a one-dimensional chain where instead the absorbing site, instead of being at the edge of the lattice, you put it in the middle. Can you get dynamics between, say, the left and right edges?
Sorry, say again. So you have a lattice and you put the absorber at the center.
Yeah.
Yeah, and then?
Could you see coupling between, say, the left and the right parts of the lattice, even though the absorber acts as like a sort of wall?
Yeah. So this also we looked at, and yeah, you can have tunneling between this. I mean, yeah, that's right. I mean, because I mean, so you can start from here, and even though the wave function can leak into the other side. That's right. So this also we studied. I mean, this is also there in our paper. I didn't talk about it.
Okay. Yeah, I'll take a look at that. Thank you.
Right. Yeah. And actually, just thinking about your other question, I mean, one way to do it is probably like if I connected a reservoir and then looked at the effective dynamics, and that should maybe okay. So I'm not sure if it will exactly look like a source, but there's a possibility it should look like a source. Okay. If I eliminate the reservoir and then write an effective dynamics.
Okay.
Hello.
Thank you.
Can I ask a question?
Yeah, sure.
Yeah. Abhishek, that the choice of the detector or the where is the detector is located, it is arbitrary, or you have some choice or preference to the detector?
No, I can put it anywhere. Like I mean, this formalism will go through if I put it anywhere.
And the sinks term is appearing because of your theory, or you are assuming that it is a sink term?
No, it will just emerge because see the every time detecting I'm losing some probability, right? So it just emerges from the
okay.
Physically one can understand it.
Yeah, so so you don't have any preference to the where the detector will be. I mean, putting a detector will disturb the system itself. So are you considering that, or whenever you put a detector in the system, that automatically disturb the system?
Right. Yeah. So that's of course, but that's the only way you can make measurements. Of course, then you can talk of weak measurements and so on, like where you try to make this interaction as weak as possible. And that's one of our like future projects, like to understand this. If you want to make some weak and indirect measurements, which are less invasive in some sense.
And I want to comment regarding the Jacob's question that if you can put two detector with having one sink and another probably the source in a balanced manner, then whole the PT symmetric scheme can be applied to your system.
Right. Yeah. No. So this was what Hatano's talk had, right? And I had this question at that time, like, is there a microscopic way to get the source term? But right now I'm not sure exactly how, but I think that's definitely interesting.
Yeah, that will be very interesting. Yeah.
Okay.
Yeah, I have a question.
Yeah, sure.
Did you check on the conditional measurements what happens to the energy of the system? How does it either increase or decrease because of the measurements, or oscillates, or what happens?
Okay, that's also very interesting, but we never looked at it. I would imagine it should increase, but maybe, but also see, okay, if it's like in a particle in a box, then it's more drastic. If it's leaking, then I can imagine that the effect is weaker and weaker. So maybe the energy doesn't increase so much. Maybe it reaches some steady value. But in the case where it's in a box and you keep making these measurements, yeah, actually, I'm not sure. So of course, you would have to look at the normalized wave function and compute its energy. I'm not sure actually.
Adding to this question, I mean, this kind of system bath coupling or system detector coupling that you had actually has the coupling is very strong, right? It's like you're putting in or taking out a huge amount of, so you're disturbing the system significantly, right? Because of the 1 by tau dependence.
Right. Yeah. That's true. I mean, yeah. So in that sense, probably we are putting in. Okay, this I'm not sure, like about what happens to the energy. I mean, one way to actually, another way to do this is to, let's say, couple my system to a qubit, like Prasanna talked about, and then make measurements on the qubit. Okay,
Right.
and there you can imagine that this is putting a strong interaction between the qubit and the system. It corresponds to making like some like you want to make pulsed, very strong pulses measuring. Okay, so of course you are not taking infinite in the experiment, but
Right.
roughly that's the limit where it might make sense.
Right. So I have just one more question. To me, this looks like effectively like a system bath or open system kind of a, not exactly, but because we are effectively getting some kind of an imaginary potential at the end. Often in open system, strong coupling limit also leads to a Markovian kind of dynamics. Would you like to comment on like what kind? I mean, is it like a Markovian?
Yeah. So I mean, this kind of limit where actually is also used. For example, this is one way to derive the Lindblad equation.
That's right, the singular coupling kind of.
Right. Yeah. So I mean, this is the precise limit where you can derive Lindblad also.
Right. Okay. Thanks, Abhishek.
Can I ask another question? I mean,
sorry, we are running out of our time, so maybe you can email him and continue the discussion. Is that okay?
Sure, thank you.
Okay, so yeah, I have actually some questions, but I will email Abhishek later. So let's thank Abhishek again, and then let's